Andreas Nautsch is a postdoctoral research fellow at EURECOM, and his talk is called How to Ask Without Speech on Quantifying Zero Evidence Speech. Welcome to the Cryptic Commons, and the floor is yours, Andreas.
Thank you. Since yesterday we spoke about deepfakes, I just want to seize the opportunity. We are also co-organizing a deepfake audio detection challenge. You can register right now. Next week, the data will be released. So that is basically fake audio recognition. Logical access means if someone hacks your telephone conversation with the online banking and plays in synthetic audio, can you detect that? Physical access, if you have seen sneakers, record, replay, can you detect that? And for the speech deepfake, everyone is using social media. I think you know where this is heading. About my presentation. So there are two things that I put on the on this. How to ask without speech. It's going in the direction of why do we even communicate? Through speech, we exchange in human communication lots of information types. And what I post there is also the inquiry. So this is more a question for the anthropologists. Children grow up, they are problem solvers. They want to interlink with other individuals, and they want to grow above their errors. They want to mature. But through school, we are more concerned about questions of what, how, and why is not so much of concern. When we ask that later, problems come of intenseness, like how are you doing this and why are you doing this? People don't like these questions. And if we then back up with privacy to the genuine inquirer, where are we heading at? Now that's more long-term perspective of the impact of privacy technology. My talk is more on the privacy zebra. That is an acronym for Zero Evidence Biometric Recognition Assessment, the framework for quantifying zero evidence. And the context here is the VoicePrivacy challenge from last year. The task was to modify raw audio such that voice biometric fails. So we should eclipse the personality trait in the speech signal. And speech recognition should still work. So we are interested in what was said, but not in who spoke. Was it the same person or a different person? As you can see, there are plenty of organizers, and it was a lot of effort on different ends. My part was on the metric side. So that is the Zero Evidence Biometric Recognition Assessment. The intuition, the background comes from forensic sciences. As a forensic practitioner, you present your evidence in front of court. And the question is really, if you validate your method, what is the benefit of evidence reporting to decision making? And how can you validate this? And why not using this for privacy? So if we talk about empirical cross-entropy, we start with some prior uncertainty, we see the evidence, and this should reduce after we see the fact. That is what the practitioner wants to do. So there should be less uncertainty with evidence than without. With privacy, if we take Shannon, perfect secrecy, we want to remain at the prior uncertainty. Now, in forensics, there's the concept of strength of evidence, so-called likelihood ratios. And there the question is more, which decision is more supported? So if the decision maker, the judge or jury, prosecutor and defendant present their evidence, pull on the string, what's the probability of voice same person, what's different person. And then it doesn't really matter how strong the evidence on each side is. It's really about the balancing of this tug of war, because that decision will be then made for. And in our setting, the judge or jury is basically the adversary. So there are two concept levels here, and I just want to go into them briefly. So this empirical cross-entropy, here's a bit of textbook. We start with prior entropy and making a yes-no decision. So what do we have? We have theta, that is same person, different person, two different propositions. The probability space is nature, the reference. The posterior that we then see when we observe evidence or scores, where I use S as a set of scores. So these are telling us how similar or dissimilar someone is. So if we compare two audio samples. And in there we have a problem, because this little fellow here is actually a thing we don't know, because in speech, that is what we use models for after all. It's not like in this Shannon paper that we can say, we know this, we don't know this. That's why we still have speech technology and research. So there's remedy to figuring out what this value could be. And we can find this remedy in cross-entropy. There we can use the law of large number and say this particular probability will be approximated by the average. the things that we are talking about here, the second probability space, is that of the classifier, so of the machine that is telling us same person, different person. And since we are in a binary decision framework, we know there's A, B, so there's a prior probability for A in the reference space and in the classifier space. We can use a literal pi to describe this. And there's the opposing thing, so 1 minus pi, the prior probability of a different person. I just want to make this short. I don't want to make this about math. I just want to make this about intuition. That's why I will use now colors to explain how the final equation looks like. The summation that we will have here is remaining as a summation. We have integrals, so discrete world becomes a summation. The average is an average. We have the negative log posterior here. We can find these prior probabilities outside of the posterior. We can find it inside of the posterior. What I really wanted to talk about is the strength of evidence, which we find here. That is what the classifier gives us in the end. And there, the score is the probability of voice for the same proposition against voice for the different proposition. And as we can see, there's some symmetry and some different treatment depending on if it's a score coming from, if it is the same person or a different one. Now, what this ECE does is it's giving us an average, an expectation over an entire population, so to say. But the real question, if we are thinking about privacy as a right for the individual, is what is the strength of evidence? So what is actually the worst case disclosure that we can have? And maybe we want not only to look into the average. So again, the analog from forensic sciences is prosecutor and defendant on a tug of war. We have the strength of evidence. And the decision maker is the adversary. So what is the worst case that we're sacrificing the individual if we just optimize for good privacy on average? And to make these likelihood ratios, which are ratios of probability, more sensible, more tangible for a human brain, the guideline for evaluative reporting forensic sciences from the European Network of Forensic Science Institutes proposed categorical tags. I now shifted the naming towards the privacy case. So if we say the likelihood ratio is 1, we have 10 to the power of 0. We could say that's a tag of 0. If we have a flat prior of 50-50, there's no updating. That remains as a flat posterior. We have the 0 evidence case. Now we can say there's a little bit more evidence. So the adversary will make, there will be more disclosure than a 50-50. If it is between 10 and 100, the adversary will make one wrong decision in 10 to 100 trials. And so on, up until one wrong decision of the adversary in at least 1 million trials. So it's a pretty strong adversary. And if you look at the scales, what you can see, here's a little gap. The anecdote goes that before the year 2000, the forensic experts were discussing up until here, and then the DNA evidence was introduced in TV media, CSI Miami aired, and then legal experts wanted to have this 1 in a million for DNA. All right, so how does this look like? If we give an example for the Zebra framework, for this audio pseudonymization challenge, where the task was speech recognition should work, but voice biometrics should fail. We are only looking now at this voice biometrics part. How much could a forensic expert still gather from this? The unprotected data is state-of-the-art voice biometric system. That's the blue line. In the green line, we see a DNN baseline of this challenge, which was explicitly trained for this. We can see it is rather close to the black profile for perfect privacy. We have in B2, in the purple profile, standard signal processing system that just squishes the speech data of everyone a bit more closer to one another. With that, the biometric information is lost. And we can see with the expected privacy disclosure as what the area of such an empirical cross-entropy would be. From quite lots of disclosure, we can get more and more towards 0 evidence. However, if we look into the worst case, the individual that we are sacrificing for this benefit, there's always one that remains in this categorical tag C within a pretty strong magnitude compared to where we started at. And that was just for food for thought. And with that, I would like to end my presentation on the privacy zebra, where the zebra with its stripes likes to confuse its predators. And so the question is, how can we do it with speech?
Thank you, Andreas. That was great and much shorter. You were well ahead of time, which means that if some people have questions or things for clarification, you are very welcome to post them. Just a few ones. I don't know if there are any questions from the floor.
Can I ask a question?
Yes, go ahead, Adrian.
Hi, Andreas. I have a question. My question is a complete outsider and being very confused about lots of different terms. Can you explain the difference to me between speech recognition, which should work, and voice biometrics, which should fail?
So there are different information types that we can communicate through speech. One thing is about what we say. So that's your question right now. Your question is not who is speaking. You know that. The thing that we were looking into, how you can preserve one information type while you completely destroy the other.
Got it.
So it's a different approach to what cryptographic usually would do, to say, I want to hide the entire signal. This is the signal will be and eventually go into the public domain. And how can you suppress, for example, biometric factors? How could you suppress gender? How could you suppress other, in this case, binary factors? And how can you measure this? And the approach there, the method that I just rushed through, is from forensic sciences, and also to give you a bit of different perspective, because what Shannon usually argues, there is these, we know the alphabet and we accept this as the nature, but the forensic scientist would say there's a bit more maybe, because we need to use model and we need to do some inquiry to it.
Got it. That really helped a lot. Thank you so much.
Yeah, great. There's a question from Michael. Do you want to pose it yourself, Michael?
Okay, I'm just thinking that was great. Adrian's question helped clarify a little bit, but I'm wondering, just as an application, if this is in a way a model of Chatham House rules. So Chatham House rules are places where one has discussions, and the rules are that one can take notes and one can report out the information content, the message content, but one cannot say anything about the messenger, about the person who's talking.
Goes exactly in that direction. So it's about hiding the biometric identity and letting the information content in. Other measures that we used in the challenge were, for example, word error rate. So how is the system doing? These were like what we call then objective measures. We also had subjective measures where people did listening tests. So how intelligible is the signal still? Like, is it useful, what remains, or is it something just white noise?
Great, very interesting.
Thank you. Thanks again, Andreas. You will have more chances to talk and develop thoughts and exchange them within in the panel discussion coming up. But so a warm hand to Andreas again.